Yes.
We have a technical problem, so we have lost the online committee members in cyberspace somewhere. The technicians are now trying to resolve this. That is the reason why we are a little late. But we have people here in the hall. So we can start anyway, and if needed, we can also finish with just the people in the hall. So don't worry. But we hope, of course, that we will be successful in our search in cyberspace. But first, I invite the first promoter, Professor Daarhoever, to open the opposition.
Geachte Promovendus, dear Vignesh, could you please summarize your research finding in a presentation of about 10 minutes?
Yes. Good morning, everyone, those who are here and also online. Welcome to my final doctorate presentation. I would like to discuss the results of my work on the physics of inkjet printing onto thin porous substrates. And I've endeavored to make this presentation accessible also to those who may not have a scientific background. Therefore, we start with this image here, and this is very similar to drawing a line with your ballpoint pen, except instead of the pen nib, you have this device on the left called the inkjet, which has the capability to deposit very small droplets of ink onto a paper. And here, instead of moving the pen, I have moved the paper towards the right, an image that we are all used to. What I want to do here is to introduce inkjet printing as a material deposition technique to the general audience and discuss briefly some of its applications. I will show you how a real industrial inkjet printing machine, huge one, works. Some of you may not have seen it. And we will look into some fundamentals of inkjet printing, what it entails, why do we need to do this, why do we need to study inkjet printing at all, because we have been printing for a long time. Very rarely that you will discard a print because it's poor. So why should we do it? And I will discuss my own work. Inkjet printing has been there for decades. What did I do here? What was our focus? And then I will leave you with some example results. Let's first start with some applications. Inkjet printing is merely a material deposition technique, and it has the ability to pattern or print things on various substrates. So you have a vast array of substrates here. You see here, we have printed something on a glass substrate, something like a graphic card image. Here, you've taken a glass substrate and printed some kind of a floral pattern. And here you see that you've taken a wood substrate and printed some designs on it, which can be used as a corkwood coaster in bars, restaurants. Here you do the same with an aluminium coaster. To make an aluminium coaster, just print some images. This is perhaps more interesting and more novel, because what looks like a 2D photo of here is actually in cross-section a 3D printed structure. What we mean by 3D printing is that you just have to print one layer on top of another layer to produce these kind of shapes. Now, inkjet printing, this is how the real machine works. You see that the turret, which is the carriage, which has the thousands of nozzles, moves back and forth, and it has the capability to exactly position picoliter size, really small drops onto substrate, producing any image. Now, this is similar to what we did, except instead of having one nozzle in the title slide, you have thousands of them. Therefore, as a poster size image can still be printed in a matter of minutes, that in reality, this movie need not have been fast forward. This whole thing could be printed actually in like 10 minutes, let's say. Now, inkjet printing may not be limited only to printing traditional things like photos or text or images, but you can print some advanced scientific things such as functional materials. Now, what we mean by functional materials is those materials that have been fabricated to have a specific purpose. For example, here is a microcircuit. It has a specific purpose. It will play a role as a motherboard in your computer. And you can have these kind of luminescent displays. So that is a specific purpose. And these kind of things have their own specific physicochemical interactions. That is what makes them special or functional materials. You see here, the example is right here. You first take and deposit drops sequentially, how you want it. In a microscopic scale, The drop displacement is 100 micrometer. So drop to drop gap. Looking at it from a macro perspective, when you look at 5 mm resolutions, you end up with this screen. The reason you have these lit up things is because if you had your droplets had some functional features on its own by nature, or if you could induce it externally by applying electric field, let's say, then you induce luminescence. This is actually an existing method to manufacture OLEDs, organic light emitting diodes, or liquid crystal displays. Inkjet printing can work very well for these kind of functional materials because it offers us high resolution. The droplet sizes are small. The droplet sizes are actually smaller or very close to the width of the human hair, so it's really small. The deposition technique is non-contact, so you don't make contact. So it is a safer and cleaner technique. And the manufacturing method itself is additive. That is, you only add the amount of materials you need. There is no subtractive process. Let us look at how inkjet printing works and what we need to print anything. First thing is that you need a droplet. And how do we generate the droplet? You see here is one nozzle tray. When you apply an electric field, these piezo materials deform and a liquid jet breaks up into drops. So electrical signals produce the droplets. Then, based on how you move, I'm sorry. I don't know what's that. Based on how you move, you can print your patterns. And how you move is controlled by print strategy. Once
You can also switch off your microphone and then continue.
Okay. Okay. Now it's on, right? Yeah. Okay. Sorry. Anyway, let's continue. So in order to print any pattern, here in this case they are printing this IETR, you need to decide how to move the substrate. That falls under print control or strategy. Then you need to process so it's not always that if you print something, the print is ready, because you need to wait for the ink to dry. Fancy term is ink processing, really. I mean, it's just waiting for the ink to dry. Why is inkjet printing a complex process? Because of the sheer variety that is there. I have only listed 2 types of ink. One is a solvent-based inks. Solvent can be water, it can be anything else. Other is a non-solvent ink, and they can be gel inks. The solvent must be supported with many additives, pigments and dyes that are the ones that give you color. Special species called surfactants. Surfactants play a variety of roles, making it easier to jet, and then they also play a role once the drops land on the substrate. Then you may use some binders which serve a purpose similar to coating. Substrate types, as we saw, can be many types, from flexible ones to paper or polymers to rigid ones like metals or glass. Once you jet and do everything that you want, you can either remove the solvent by evaporation, or if you are using the gel ink, you may pass UV light and solidify your deposited material to obtain the final print. Fluid dynamics entirely controls the inkjet process. Here you see snapshots of a drop being formed from column of ink from the nozzle, and properties such as surface tension and viscosity govern how nice a droplet can be formed. If you have a too viscous liquid, you may never form a drop. If your surface tension is too low, you may never break up into one single droplet. Once the drop lands on the substrate, depending on what the substrate is, different kind of interactions can occur, and a droplet will spread until evaporation stops it from spreading. Eventually, the print is dry and ready to use. Now, one of my objectives here was to develop methods to quantify liquid content when ink drops become distributed into paper substrates. And paper is a very complex material, because what looks like a smooth surface from a macroscopic view, really, if you look into this under a microscope, you will see there are a lot of crevices called pores, and the fibrous nature makes paper permeable by itself. So what do we really do, what does any physicist do, is that first you must develop some experiments, because you don't know what the problem you are studying, and you will try to measure a particular quantity of interest. Then we have to understand what we did, so we call that data analysis. Really, data analysis is just looking at the results and understanding what is going on. And then that's not often enough. You have to develop precise insights, and there you may have to do some mathematics. We call it numerical modeling. This is the golden formula for anyone who is in science, not just me or a physicist, for anybody in science. Here's an example of one of the methods, is that we want to understand if you want to measure liquid distribution in paper, what we did is we pass light through wet paper, and what is plotted is the intensity, or how bright or dark the paper is as a function of amount of liquid you add. So you see that the paper becomes darker with decreasing amounts of liquid. So when you have more liquid, your paper is more brighter. As an example result, I take the inkjet that is black here, and I move the substrate at a fixed speed, keep putting drops, and then you will form a line like this. Here, if you reduce the amount of drops you add, your line becomes narrower and also shorter, as you expect. This is what should happen. Here you see that here you are more brighter because more liquid is there. Far away, you are darker, exactly like the previous slide. This is called optical imaging. It's just like seeing with your own eyes. This is a different kind of imaging. It's called thermal imaging or infrared imaging. And this is the same. Because water evaporates, temperature of the paper reduces. It's the same effect as if you have sweat and walk into an air-conditioned room, you feel colder. It's exactly what is going on. Here is an infrared image of your hand. It could be anyone's hand at any given time. And the reason why we are using this is because every object emits heat. This is the principle behind night vision goggles. This is also why they put now thermal cameras in airport to monitor temperature, something we are now very much used to. With this, I want to thank my PhD advisors, Anton Darhuber and Jos Segers, and the funding organizations, NWO and Canon, for their generous support, and all the audience who watched this presentation. Thank you all very, very much.
Okay, thank you very much. Professor Darhuber, are you satisfied?
I am satisfied.
Thank you very much. I just got a message that the external committee members can see and hear what we do here. You can leave your mask off. Everything is visible and audible to them, except that we cannot see or hear them. So we are trying to find a solution. But in order not to lose time, I will change the order, and now I invite the secretary of this committee, Dr. Peerlings, to continue the opposition.
Thank you. Thank you, Mr. Chairman. Geachte promovendus, first of all, congratulations on completing your thesis. I enjoyed reading it. I learned quite a few things from it, so that was a pleasure. But of course, I've been hired to also ask some questions on that thesis. And as you may know or may not know, my interest is in the water uptake into the fibers and then the consequences from that point onwards, mainly. So that is the part that I would like to discuss a bit more with you. And I saw that in the modeling that you use, you model this part, so the exchange of water between pores and fibers in chapter 4, but not in chapters 2 and 3. So I was wondering whether it's irrelevant in chapters 2 and 3, and how relevant is it when you add surfactants, which is what you do in chapter 4. So what is the importance of this term quantitatively, I guess?
Thank you for your question. Really how this progressed was that the modeling was done in a step-by-step fashion. And all the papers are actually, the first paper was done by me, the second chapter was first year work, third, second year work, fourth chapter, third year work, and so on. So in the first, we didn't want to make the problem more complicated by adding also the 4-fiber exchange in the model. This is why you see it is not there in chapters 2 and 3. But when surfactants are part of the problem, when we did experiments also with surfactants, it became clear that they are doing something new, and that pore fiber exchange must be an important part of the problem. Otherwise, there is no point in doing any model with surfactant. We could just show the old pure water model, it would work. So this is the reason why we did it. But I think surfactants play a crucial role in deciding how the liquid is distributed from the pore to the fiber. And I think we discussed in the chapter 4 that there is also the cause for the hypothesis I have is that it is the cause for the intensity overshoot we measure with surfactants, which was simply not there with pure water. So I think I have answered the question.
Yeah, so quantitatively, could you maybe comment on how important the loss of water from the pores to the fibers is compared to evaporation, for instance? Is this a
for example, yes, that is discussed in page 97. So in order for the liquid to be distributed from the pore to fiber, the surfactant must get absorbed, and once it gets absorbed, it leads to the non-monotonic moisture distribution.
Mm-hmm.
And I think they are competing phenomena, absorption and evaporation, because here we devise a time scale which shows that tau absorption, page number 97, table 5.1, tau absorption is expected to be in 10 power 3 time scales, also tau evaporation, which is also 10 power 3. But here, I think, since they are competing phenomena, I would say both equally determine the fate of the final print.
But the time scale doesn't tell me the magnitude of the effect, right? So that they happen on the same time scale is one thing, but how much water do I lose by evaporation, and how much do I lose in quotes, I guess, because you may wanted to go into the fibers.
Yes. So we saw that the role of surfactants in reducing changing the evaporation rate might be negligible in itself. So surfactants are really not altering the vapor pressure of the liquid that much to have a crucial effect. And also, if you see our thermal amplitudes, we are always in 6 Kelvin. So evaporation is going on depending on the concentration gradient and what the surrounding gas phase is doing. That is apparently controlling it far more. For the fiber exchange, it has been very difficult to quantify because the optical contrasts that surfactant leaves are small. Therefore, I found it very hard, and the presence of this intensity overshoot also complicates the analysis. So, time scale wise, or quantifying how much liquid is going into the fiber and how much is lost to the environment is not that much trivial at this moment.
I understand. And you're talking about the experiments now, I guess, right?
Yes.
What does the modeling say about this? Because there it should be easy to extract this data.
That's true. Well, the model which really includes everything, because some models simply don't take into account absorption, is shown in 4.15. And there, I think we have not yet split effect of evaporation separately in this chapter.
Okay.
That is true. Yes.
And would you dare to predict? I understand why the water uptake in the fibers is not in the earliest chapters. You explained that clearly. But suppose you would go back now to those cases with pure water, no surfactants. would you dare to predict how much of effect it has there?
My guess would be that, if I'm right about the hypothesis, that surfactants delay the process of liquid going into the fiber, and that it would remain in the pore space longer, then you will also lose more to evaporation.
Mm-hmm.
So if you have surfactants in the system, then and if you don't have surfactants, you do everything the same. I expect that evaporation effect will be stronger for the surfactant gas because liquid will be more in the pore, will remain in the pore spaces for a longer time. Once it goes into the fibers, it may be hard to lose it to the gas phase. So absorbed moisture on the fiber may not be lost into evaporation easily. So surfactants should give us more evaporative losses, is my guess.
But can I also translate that to conclude that in the earlier chapters this effect would have been important as well?
Sure. But that one studied pure water without surfactants.
Yeah, I understand. But for the pure water, is the absorption into the fiber an important?
I think it's equally important, yes.
Equally, yeah. Okay.
We didn't do it because it was too complicated at that time.
I understand. You're cleverer now. Okay. Do I have time for more questions, Mr. Chairman?
If you make it a brief question and you give a brief answer.
That depends on the question.
Okay. Well, still about this uptake into the fiber. Well, how do you imagine the physics? So in a model, you model this with a dual porosity model, which basically means that it's capillary pressure driven, right? Is that really what happens in the fibers, or at some point, I would imagine that the water also needs to go into the polymer network and make the fiber swell, right? So I'm just wondering, is this the correct physics? What are your thoughts about this?
I think the pore fiber distribution is governed by the fact that the fibers are permeable and they have a higher absolute capillary pressure. And the swelling, while it has been a feature in the experiments, has been a challenge to incorporate it in the model. First of all, there is not yet a clarity on what modes of swelling we should have, because apparently the modes are decided by moisture gradients that are induced. But my colleague tried a simpler approach first to introduce swelling, but it became quite complicated. But since in our models we are integrating the thickness direction of the paper out, I think the physics still is quite solid, and we see most of the features, at least qualitatively, from my experiments.
Okay.
So I'm happy with the level of physics in the chapter 4.
Well, good to know that you're happy. Thank you very much.
Okay, thank you very much. First of all, I would now like to point out, to say that the Eindhoven University of Technology is also very grateful to the external people in this committee. We are grateful that they are listening and hopefully also speaking. In this committee we have Professor Mugele of the University Twente, Dr. Den Otter of the University Twente, and Dr. Tomaseu is from Canon but also TUE, and Professor Weishoff is also TUE as well as Canon. But anyway, I thank all of you for being here, and I will now try to give the floor to Professor Mugele. We cannot see you, but maybe we can hear you. So if you can try to open your microphone and ask a question, we will find out.
Thank you, Mr. Chairman. Can I get a nod or any reaction from the committee? From the people in the room? It does not seem to be the case.
So we will then invited the external committee.
Hello?
The external committee members to email me the questions. So that's why I'm having the telephone. I'm not checking anything else. So I'm waiting for email questions.
Online.
Okay, very good. I would suggest that we continue with the next opponent, and then I'll prepare my questions.
Well, we will buy some time by first proceeding with Professor Wijshoff. Please, could you continue the opposition? Then we'll find out a way how to get the questions of the external committee members in here.
Okay, thank you, Mr. Chairman. Geachte promovendus, first of all, I want to thank you for the work you have done about the beautiful physics of inkjet printing. It's a subject which keeps me busy for more than 25 years by now. And it's always very nice to see that some clever young people are still able to find a lot of new insights. And to learn even more about this, I would like to ask you some questions going from front to back to the thesis. And let's start on page 13. There you describe the experimental setup. And for the thermal measurements, it's very important that you know the emission coefficient of your material. And you noticed that you could not detect a significant effect of the moisture content on this emission constant. Mm-hmm. How were you able to draw this conclusion? Because moisture evaporation is always present.
Thank you for the question. So how we took care of the emissivity doubt, so the real question was really that can you trust what the camera is showing? Is that I also had the same question. Camera is showing me a temperature. Is that the real one? How I did it was that we had a precise temperature control, equipment, like a hot plate. Yes, it's a hot plate where you can set different temperatures. And then I keep a paper on it. Then I wet the paper. But I also induce contact between the hot plate and the paper, so you can see that you have made contact because of the moisture, and because of that the thermal conductivity of the plate you can correctly detect the temperature. So it will go to the hot plate temperature. That part which has made the contact, which is in contact, will have the thermal conductance of the hot plate, so you will see that it has exact same temperature, or whatever with the camera's error, that you will be having the same, whereas the other parts that are not fully in contact will be getting colder and colder due to evaporation. This shows us that we don't know really the emissivity of paper, let's say, not to the great extent precision. Therefore, these kind of tests gave us the confidence that we are in general measuring roughly the correct temperature. And another advantage that I had in these problems is that rarely you are interested in the absolute temperature of anything. You are rather interested in the temperature difference. And the delta T, again, it's not super crucial to know exactly the emissivity of paper.
Yeah, because even when you have a very good thermal contact between hot plate paper with a lot of water, I think the emission is really from the top part. So when you have evaporation, the absolute temperature can still deviate from the top part of the paper, I guess.
But not if you don't have evaporation only plays a role when you don't have good thermal contact. That is fine. But to check if your camera will always show the correct temperature, you can do it only in one part, and then if that matches with the hot plate temperature, because that you control and see, then I trust that then you can use the camera and believe mostly what it says. Instead of working very hard on a pixel-to-pixel calibration, this was a shorter way to do it.
And when you focus on thermal differences, then this will be less.
So I will not call what I did as calibration. It is not. It could have been done greater, but we didn't want to spend time on pixel-to-pixel calibration for this purpose. This is more than enough, I think.
Okay, thank you. Then I go a little bit further. On page 17, it's about the model. I know that Frieder Mugele has quite some questions about the model, but there's one thing I want also to stress out here already. On page 17, you say we do not have to take into account hysteresis. But you are modeling evaporation, but also condensation, which is about moisture going away from the paper, coming back. Do you not have to take into account hysteresis for that then?
It would be great to take into account hysteresis. It would be amazing. But it was, first of all, it was too complicated. The reason I think I'm justified not doing so is because the wetting front, I don't have the pen for this, so the wetting front is in a steady state. The wetting front position, the experiments are designed to not move the wetting front under the Darcy regime. You are only changing it by the substrate motion. When the wetting front is steady and a fixed moisture distribution exists, then you are more justified not introducing capillary hysteresis, because it makes sense only when things are moving. Capillary hysteresis stems from contact angle hysteresis. But if you keep it stationary, the wetting front, then evaporation and condensation only inducing local changes. They cannot alter the position of the wetting front. So there is no need to, or I thought there was no need to introduce hysteresis and make this already complicated model way more complicated.
So you say because we have rather low speed, we have full penetration of the moisture from top to bottom, and we only look at lateral displacement, then you do not have such a big effect of hysteresis.
The lateral displacement also is not spontaneous. It's rather the forced inhibition of the substrate moving. Therefore, hysteresis is not going to affect much in the results.
Okay. Then let's go a little bit further on page 20, where you describe this heat absorption, and you come up with a power law for that. But when I want to connect to physics, it's about equation 2.19. When you would connect to physics, I would expect terms like the interfacial energy between the liquid and the solid, this amount of specific surface area per volume, and these kind of measures. So how can you connect to the real physics of wetting and with this equation?
Well, I agree this is an empirical formula. Actually, this is not a real physics formula. 2.19. 2.18 is solid. 2.19, however, is just an empirical tool. Somebody did experiments on similar materials like paper, maybe even paper. We have to look at reference. But there they have a fitting curve, and that is this curve. Let's say C1 exponential amount of liquid C2. And all the terms like interfacial area and the contact angle, they are all included, comprised in these terms C1 and C2 somehow. But I agree that it is not done from the first principles. 2.19 is not developed from the first principles, rather a fit of someone's experiments that we took.
So basically it's a fit function you have to do for each combination of a liquid and a certain pH.
Yes, you have to evaluate C1 and C2, I guess, by doing experiments.
Okay.
Not a theoretical developed story, let's say.
But still connecting to the physics then, on page 24 you make a remark about this heat absorption. And there you state that why is it more pronounced at a low saturation value of the moisture content? So why is heat absorption more pronounced when you have a low amount of saturation, of a low amount of water inside the porous material?
Yes, so the reason is that at very high moisture contents, so the heat absorption fundamentally stems from absorption of some species onto fiber of paper. Now at very high moisture levels, let's say I fully wet the paper, the tendency will be to evaporate. Therefore a bulk phenomenon takes over than a surface phenomenon of absorption at huge amounts of moisture. So if you take a paper and dip it into paper, and if you see from the infrared camera, you may not see the heat. You will see it is cooling down because of evaporation. However, if you put a spray of liquid onto paper, and if you see from the camera, you may see spikes of temperature because small amount of moisture will absorb. Beyond that, you start to enter the bulk regime where condensation and evaporation can happen. Condensation is a bulk regime, but not heat absorption itself. That must stem from absorption, which can only happen at low values of moisture content. That is the argument.
Okay. Thank you.
Thank you very much. In the meantime, I have received some questions from the external committee members. First, Dr. Dan Otter. Congratulations on completing your thesis. It discusses a complex problem and I enjoyed reading it. In Chapter 4, you extend the model of Chapter 2 with surfactants and absorption into the fibers. You write that for the pores, you adopt the Van Genuchten equation. Specifically, you only mention a reduction in the maximum water absorption in the pores, but the surface tension plays an important role in Richard's model, and you now reduce this tension by adding surfactants. How are they accounted for in your adoption of Van Genuchten?
You could thank him on my behalf. Unfortunately, I think those parts I did not write it in my thesis, and so it is a very good question in that sense. We have applied a linear function that makes surface tension decay as a function of concentration. So when you have zero surfactant concentration, you have the same surface tension of pure water, and as your concentration goes down, we have supplied a linear law, that a linear fit, let's say, that decreases the surface tension until you reach the critical micelle concentration. Then you are constant. Beyond CMC, you will not change surface tension. So that is how it is taken into account by a linear, simpler linear fit, which for some reason I had forgotten to add in the thesis, for which I apologize.
Sorry. In Chapter 5, you study the spread of dyes. Your experiments and simulation focus on the front of the dye, but for printing it would also be relevant to look at the homogeneity of the dye behind the front. How homogeneous is the dye distribution?
Yes, I think this is somewhat handled in the all of the discussions. Color density is the parameter that in principle describes the homogeneity of how dyes are spreading, and we have done that. For example, is discussed in the last section discussion under dye precipitation, and we explain the cause why you have stronger color density for fluorescein salt, that is figure 5.9 A to D, which changes. So the color density is maximum at the footprint area of the droplet. That is what the section 5.5.6 talks about. Whereas it's not so for the other kind of dye, rhodamine. So it's handled there in a different way. And during inkjet printing itself, we have shown that the homogeneity of the dye distribution depends on several parameters, and they are discussed in the section 5.5. And so the whole goal was to discuss when you change the parameters, what happens to the distribution. So that is also in part taken into account, how the color density or the homogeneity changes. So I think in all the sections it is touched upon, but rather I would not say it is the key focus of the chapter. But it surely plays a role.
Okay, thank you. Dr. Otter can also reply a comment. He is able to hear you and see you. You cannot hide from him.
So he's able to hear me?
He can hear you.
Okay, great.
So it's, he can hear you, and I hope that he will send me a remark, an email, that he either or not agrees. In the meantime, well, Dr. Otter has also sent me a next question. Let's first do this before we continue with Professor Murali.
Mm-hmm.
But first, the third question of Dr. Otter. In figure 5.9, you show an interesting experiment on the spreading of a droplet containing dye. You observe a marked difference between the cationic red dye and the anionic green dye.
Mm-hmm.
You attribute this to the presence of calcium ions in the coated paper, which interact with the charged dye molecule in the ink. Did you perhaps also try the same experiment with uncoated paper, which does not release ions? And what would happen for a non-charged dye on this coated paper? Is it important that the calcium ion is 2 plus rather than 1 plus?
Okay. I think it's a brilliant question. I don't know if I know the answer, but I think if you do not have a positive ion, so the reason for this, in short, if you want me to say it in a nutshell, is that effective color fixation occurs when you have opposite charges, so the dye and the substrate. So if you have the same charge, this is also why the rhodamine pink color dye doesn't have it, because they don't have the opposite charge attraction. So if you don't have Ca2+, I expect that fluorescein also does not precipitate in paper. So you should not have this in principle. But I never tried it myself because we never had a really non-coated paper. For this reason, we didn't try. I think if it's 1 plus, my current naive guess will be that the effect will be less stronger, but should exist. That is my answer.
Okay, thank you very much. Now I will now change identity and start speaking on behalf of Professor Murali. The first question of Professor Murali is, first, congratulations on an excellent thesis that couples well-controlled experiments with detailed modeling. Really impressive. The system is very complicated. Let me try to simplify. Questions are in chapter 2. The inset of figure 2.5a shows saturation of position of the liquid front for low speeds. Did you see this experimentally too? I missed it in the figure 2.3. Is there a cover to suppress ambient airflows in the setup?
You could again thank him on my behalf for the questions. Yes, so in 2.5, we established a steady wetting front from the simulation. So page 24, figure 2.5a. It doesn't become steady straight away, but we are showing the results after it has become steady. And after that, the substrate is only moving into the wet zone. Therefore, the wetting front cannot advance ahead. Yes, indeed, we see this in the experiments. For example, the figure shown in 2.1c is one such snapshot. And if I play the movie, there must be in my laptop somewhere, we will see that the same position of the front will be present, and that you are doing really the same. And yes, there is this whole setup in figure 2.1b is kept inside a plastic box with one opening. So external airflows the one opening is just to put my hands to do experiments, and we can also in principle close it during an experiment. So yes, in principle there is a cover, and external airflows do not, that is anything away from the box, do not affect the measured data. That's the answer.
Okay. Thank you. The discussion in chapter 2 is all based on T variation. What if you keep the temperature constant? Do you expect saturation too?
Sorry, can you please read it again?
Yeah. The discussion in chapter 2 is all based on T variation. I assume T is temperature. What if you keep the temperature constant? Do you expect saturation then too?
So you expect saturation 2 to be a constant?
If the temperature is constant, do you then also expect saturation?
Not really, because saturation is the amount of liquid content. While there is a link between moisture content, in this chapter we call it SW, and temperature, if you change temperature, the effect that it would have on the moisture content, the saturation SW, is rather negligible. So if temperature is constant, you still have to do work to keep the wetting front constant. And but I don't fundamentally understand how can you keep temperature constant if water will evaporate and it will cool down the substrate. So how to keep temperature constant, but despite having liquid there. That I don't really actually understand. Temperature cannot remain constant if you put liquid onto paper, because it will evaporate, as the question of Professor Weishoff.
Okay. A further question. How does the saturation value of XD vary with vapor pressure? What do you expect for non-volatile fluids?
That is another great question. So for non-volatile fluids, I expect that both evaporation and condensation will not occur because they cannot evaporate. Therefore, they can also not condense. Therefore, only the heat absorption will be there. So if you look at the math equation, 2.18 Q dot is whatever. The term J, LW goes out, 0, because no evaporation. Therefore, also no condensation. Every other term would remain. And then the only thing that will induce heat is the last term, phi rho W U sub TSW dx. So without evaporation, the amplitudes of this curve will be smaller. And in terms of XD, I expect you only have one regime, that it will scale linearly with, it will scale inversely to U sub. So the second regime where I draw a line in the inset of figure 2.5, I expect that will be the only regime and not the regime where it's constant for non-volatile fluids.
Okay, then the last question of Professor Murali in this row. Page 28. You say things depend on buoyancy due to evaporation. Could you envision an experiment to suppress airflow? Would you still get a steady state?
Yes, if there is airflow dominant in one direction, then I don't expect strong effects of buoyancy. In this experiment that I did, there is no induced external airflow. Therefore, buoyancy, because water vapor is lighter than air, you see all this circulation. You can't really see it, water vapor is invisible. But if you have a predetermined airflow direction, then you should not have it. Buoyancy should become again negligible if you have some airflow already present. For example, if you would give a channel flow on top of the substrate, like a Poisson flow, then buoyancy should be suppressed, yes.
Okay, well, Professor Murali sent a lot of questions, but I'll ask just one for the moment. Your current employer does not make its money by printing at 10 millimeter per second. What are the fundamental problems in extending the model to a higher printing speed?
No, actually, it's not in the model, the problem. It's in the experiment. We cannot really do what we did with the printer. First, we don't have it. I don't think Canon, formerly OSE, wants to give us this machine to play in the lab. That is the real reason why we don't do it. But I think the speeds are just numbers. That physics-wise, there are really no huge differences between what I did here and what really goes on in real printing. So I have one nozzle jetting at 1000 hertz, but they have thousands of nozzles jetting at 10 kilohertz. Therefore, they move faster. So if you take everything into account, I am somewhat far away from the real regime, but the physics and the principles governing how to understand printing on paper to a large extent remains the same. That is my current conclusion.
Okay. Let's conclude now for the moment the questions asked by Professor Murali, and we can continue with the questions forwarded by Dr. Tomazeo. And maybe first we have to inform the Beadle that because we started 7 minutes late, it would be okay if we ended 7 minutes after 12 o'clock. So, Mr. Secretary, if you could warn the Beadle, and we will have a proper hour for the defense, because now Dr. Tomazeo is taking off. Congratulations for your interesting and inspiring results published in your PhD thesis. I am happy that finally we are in a position. In chapter 2.3, you discussed the temperature distribution in time and space, X direction, for various phases of the paper speed. Consistent results are presented in figure 2.2 for for uncoated paper, where you show the two main parameters, dt max and dx max. These results are a function of substrate speed are, for my knowledge, for the first time presented in publications. I would like to ask you to comment on the results from figure 2.3, where dt max has a maximum for the used substrate is 1 millimeter per second, and the x max shows a kink point.
Yes. Once again, you could thank Dr. Thomas A.U. on my behalf. Yes, so the evaluation of the curve 2.3a, let's say, delta T max as a function of U sub, clearly goes through more than one regime. And because we have so many things in the model governing this, like buoyancy and the porous media and the gas phase interactions, it has been impossible to scale and say how the delta T max scale as U sub. But my understanding is that at very low speeds, temperature changes are halted. They cease to depend on U sub because buoyancy is the dominant mechanism. If you had saturated, the cooling had saturated simply because your wetting front has progressed far because U sub is small. As you increase, the direction of the gas phase begins to align with the motion of the substrate. That is, substrate motion begins to control also how the gas phase direction is aligned. So you go up because you are strongly wetting the dry paper moving the dry paper into the wet zone. So then there is an increase regime between a range of U sub, let's say from 0.1 to 1 mm per second. You induce local maxima simply because somewhere the evaporated vapor can come back and condense. If you go too close, things like thermal conduction start becoming important, and then you decrease and you also reach asymptote at U sub equals 5. I think the same argument explains the figure below, delta X max, because for low values of U sub, because of buoyancy, you have a different scaling of the width of the temperature curve, delta X max, and for high speeds, you are controlled simply by U sub, and that is as expected. So because of buoyancy, the curves have different regimes. That is my answer.
Okay, now a long question about the inspiring results obtained via light transmittance versus liquid content into paper, figure 3.3, page 38. The calibration curve is absolutely necessary for a good interpretation of the measured results. Although you don't specify what liquid has been used in figure 3.3, you do discuss in chapter 3.2.3 about the maximum liquid holding capacity for two polar liquids, water and EG, and a non-polar one, hexadecane. You discuss your experimental data in terms of swelling of the cellulose fibers. Is the imbibition into fibers playing a role in this QL max for water, where the QL max is 1.22, and EG where it is 1.11, and hexadecane where it is 0.46?
Yes. So the first question was, what is the liquid that was used for 3.3? Answer is water. We also used so the same images were made with other liquids, but I think the one published here is the water one. Then he asks, yes, I think the difference comes between the value theta L max is very close between water and EG because they are similar types of liquids. Both of them have, I think, similar polarity. And hexadecane is completely non-polar, therefore it has strong non-wetting properties. So it has a smaller value, and therefore it cannot swell the paper as much. So I think swelling is important, and I think that is why we see all these differences between different liquids. So yes.
Okay. Do you think that this method can reveal a possible separation of water and EG into paper from a mixture of the two liquids?
Yes, I think it has the potential to work, but you must calibrate separately the mixture of EG and water, and then we must hope that there are enough optical contrasts that such that you can see where is EG and where is water. But I think there is a chance and it can work. That is my
Okay.
One has to try.
Yeah. Thank you very much. You have found a new separation method then. We will now continue with the co-promoter, Dr. Zegers.
Thank you, Mr. Chairman. Geachte promovendus, so I would like to congratulate you with your fine thesis that you completed even before your contract ended. And it's also very nice to see that you had already published some of your results in authoritative journals. So congratulations also with that. I have a question specifically related to the fact that you are now working, of course, also at Canon, so you know about the practical implications. And let's say if you look to page 68, for instance, in your thesis, that is then 4.4 figure, then you see that in many of your figures that an abundant amount of liquid is jetted on your on the paper. And so this is a typical example. Let's now go to, let's say, figure 43. There you have figure 3.8. Where you also have a variety of, let's say, of speeds that you apply, and the variation in speed means also the amount of liquid that is jetted on the paper. Now, my first question to you is, what is a representative situation for practical cases of printing? Which of these graphs do you think are representative?
Well,
so which speeds are representative?
As I told just a few minutes prior, it is not crucial. So this 0.05 millimeter per second is a choice that I am forced to make because we work in a laboratory. That is, and we have, so our printhead that we saw in the presentation is only capable of delivering, let's say, the maximum it can do is 1,000 droplets a second.
Yeah, but
if I move very fast, then we see nothing.
That's crucial, yeah. So, to my opinion, you can do experiments that are exactly in agreement with what is being done at Canon. Because,
if you give me the real thing, yes, why not?
In principle, but you need your thermography to see something, yeah, which will form the starting point of your research work, yeah.
Yes.
So, if I let's say you print a piece of paper at home and you magnify it with a magnifying glass, you see that the paper is generally not always completely full with dots of ink. So,
well, you can do that if you want.
Sorry?
You can print anything you want with a real machine.
Yeah, so, okay. So, are all these curves then representative for the situation that there is at a practical printer or not?
I think so, yes, because in a practical printer, while you may want to print some Mona Lisa picture, yes, you can do that. That is not even a problem. If you want to study some problem, if you want to understand how a new type of ink interacts with a substrate, whatever the substrate is, you will start, I think, a problem by studying lines. Because lines are fundamental structures. Lines are useful to understand because they really determine the usefulness of an end product. If you don't print a line and it doesn't look like a line, then there is no real use in printing Mona Lisa. Therefore, I think whatever you do, you will print such lines. You may move at a different speed because for example, in the real printer, it may move at meters per second. Reason is that they jet with thousands of nozzles simultaneously at somewhat higher. So it's all reasonably compensated. While this is somewhat away from the real regime, but not that much. But all the methods and the mathematics governing this are also, in my view, very close to the real process. Yes.
In the equations, in the chapters 2 and 3, temperature plays an important role. It's not for nothing, of course, because temperature is detected in your experiments with your infrared camera. So if you know the temperature, you can, let's say, analyze and understand the images that you have. But in many of your experimental results, the temperature is only varying a little bit. Yeah, you can also see that in this figure 3.8. For instance, for the settings of 5 millimeter or 2 millimeter per second, your temperature is changing something like 1 Kelvin. So that is really, that's very small. Now my question is, you set up your equations where temperature is analyzed in a lot of detail. Is it now not possible to simplify your model a lot by saying, okay, my temperature is constant, and then simplify the equations and have an easier way of predicting the transport, for instance?
But temperature is not constant.
No, but I'd say it is only varying, let's say, 0.5 degrees. So that's really, it's a small amount.
Yes, but I think the more interest from the modeling standpoint was not to really predict the absolute magnitudes, rather get the shapes or how the temperature is varying, even if it's a small magnitude, because that determines also the ability to convert from TE to theta W. For example, if you can predict things like as you move at high speeds, you see that the coldest point is closer to the end of the line.
Yeah.
This may be very crucial to predict from an industrial perspective, in my opinion, because if I look at an infrared image alone, in a real printer, it is really difficult to do the optical imaging. While it looks like easy, you can take a photo. But the infrared, if you mount it somewhere, if you know that the coldest point is at the tip, for example, you may now know that something that you printed ends there. So more value, in my view, is not in caring that much about the amplitudes, rather the shapes of the curves. Therefore, we have to really simulate it. Otherwise, we will miss out on important insights, I think.
Yeah, but is there something that you could simplify in your equations? If you take your temperature constant, isn't then your full analysis not a lot simpler?
Sure, indeed. Then you solve only one equation instead of two.
Yeah.
So it's, yes. Well, one may choose to skip temperature if they are not looking for these kind of insights. But here we are. So we did both. But in principle, just simulating the theta W may suffice, depending on the application that you want to do. Yes, but if you don't do temperature, your life will be more easier, indeed.
Okay, but you did not consider that, to do that?
I think
if you look into your thesis, it's I know that it's a very complex problem. You have all these coupled equations, but this makes life very complicated. But then to simplify things, that would be then also, and to compare it with the complex model that you've derived, I think that would be next step, or not?
Well, I followed what the promoter wanted. I cannot tell him.
Okay.
Then I won't be here then.
Okay, I'm satisfied. Thank you very much for your kind words.
Thank you.
Thank you very much. Dank u wel, meneer de Pedaal. I also would like to thank the candidate for being so flexible and this sort of improvised ceremony with 103 people in the online audience. That is, I think it is a record in our department. So everybody has seen you. We are now, the committee is now retreating for deliberations, and I will adjourn the session, and we will return in 20 minutes or so. The session is adjourned.